Welcome to the session Hyperbolic Functions and Inverse Hyperbolic Functions. Hyperbolic function. A function y is equal to f of x is a transcendental function of x if it satisfies no equation of the form Pn of x into y raised to n plus etc. plus P1 of x into y plus P naught of x is equal to 0, in which the coefficients P naught of x, P1 of x, etc., Pn of x are polynomials in x. Functions that do satisfy an equation like Pn of x into y raised to n plus etc. plus P1 of x into y plus P naught of x is equal to 0 are called algebraic. For example, the function y is equal to 1 divided by square root of x plus 1 is algebraic because it satisfies the equation x plus 1 into y square minus 1 is equal to 0. Here the polynomials are p2 of x is equal to x plus 1, p1 of x is equal to 0 and p0 of x is equal to minus 1. Polynomials and rational functions are algebraic, and all sums, products, quotients, powers and roots of algebraic functions are algebraic. We could have defined the transcendental functions to be the functions that are not algebraic. Here we shall discuss the hyperbolic functions and inverse hyperbolic functions. Both are transcendental functions. Every function f that is defined on an interval centered at the origin can be written in a unique way as the sum of one even function and one odd function. The decomposition is f of x is equal to f of x plus f of minus x all divided by 2 plus f of x minus f of minus x all divided by 2. Here the first term is the even part and second is the odd part. If we write e raised to x this way, we get e raised to x is equal to e raised to x plus e raised to minus x all divided by 2 plus e raised to x minus e raised to minus x all divided by 2. The even and odd part of e raised to x, called the hyperbolic cosine and hyperbolic sine of x respectively, are useful in their own right. They describe the motions of waves in elastic solids, the shapes of hanging electric power lines, and the temperature distributions in metal cooling fins. The center line of the gateway arc to the west in St. Louis is a weighted hyperbolic cosine curve. Just as x is equal to cos u and y is equal to sin u are identified with points x, y on the unit circle, the functions x is equal to cos h u and y is equal to sin h u are identified with points x, y on the right hand branch of the unit hyperbola x square minus y square is equal to 1. Definition and identities. The hyperbolic cosine and hyperbolic sine functions are defined by the equations cos h u is equal to 1 by 2 into e raised to u plus e raised to minus u, hyperbolic cosine of u, sin h u is equal to 1 by 2 into e raised to u minus e raised to minus u, hyperbolic sine of u. The remaining hyperbolic functions are defined in terms of sin h u and cos h u as follows. Tan h u is equal to sin h u divided by cos h u, which is equal to e raised to u minus e raised to minus u all divided by e raised to u plus e raised to minus u. Sec h u is equal to 1 divided by cos h u, that is equal to 2 divided by e raised to u plus e raised to minus u. Cot h u is equal to cos h u divided by sin h u, that is equal to e raised to u plus e raised to minus u all divided by e raised to u minus e raised to minus u. cosec hu is equal to 1 divided by sin hu, that is equal to 2 divided by e raised to u minus e raised to minus u. Also, we have following identities of hyperbolic functions. Cos h square u minus sin h square u is equal to 1. 1 minus tan h square u is equal to sec h square u. Cot h square u minus 1 is equal to cosec h square u. Cos h u plus sin h u is equal to e raised to u. Cos h u minus sin h u is equal to e raised to minus u. Also, the hyperbolic cosine is an even function, that is cos h of minus x is equal to cos h of x. And the hyperbolic sine is an odd function, that is sin h of minus x is equal to minus sin hx. There are major differences between the hyperbolic and the circular functions, however. The circular functions are periodic. Sin x plus 2 pi is equal to sin x, tan x plus pi is equal to tan x, etc. But the hyperbolic functions are not periodic. Identities. Sin h x plus y is equal to sin hx into cos hy plus cos hx into sin hy. Cos h x plus y is equal to cos hx into cos hy plus sin hx into sin hy. This in turn give sin h 2x is equal to 2 into sin hx into cos hx. Cos h 2x is equal to cos h square x plus sin h square x. From this we get the formula cos h 2x plus 1 is equal to 2 into cos h square x. Cos h 2x minus 1 is equal to 2 into sin h square x. When we substitute x is equal to u by 2 in the above two equations and take square roots, we obtain the formulas cos h u by 2 is equal to square root of cos h u plus 1 divided by 2. Sin h u by 2 is equal to plus or minus square root of cos h u minus 1 divided by 2. Derivatives and integrals of hyperbolic functions. Let u be a differentiable function of x and differentiate sin h u is equal to 1 by 2 into e raised to u minus e raised to minus u, cos h u is equal to 1 by 2 into e raised to u plus e raised to minus u with respect to x. Applying the formulas, d e raised to u by dx is equal to e raised to u into du by dx, d e raised to minus u by dx is equal to e raised to minus u into d by dx of minus u, that is equal to minus e raised to minus u into du by dx. We get d by dx of sin h u is equal to cos h u into du by dx, d by dx of cos h u is equal to sin h u into du by dx. Then if we differentiate y is equal to tan h u is equal to sin h u by cos h u as a fraction, we get d by dx of tan h u is equal to cos h u into d by dx of sin h u minus sin h u into d by dx of cos h u all divided by cos h square u. That is equal to cos h square u into du by dx minus sin h square u into du by dx all divided by cos h square u, which is equal to cos h square u minus sin h square u into du by dx all divided by cos h square u, which is equal to 1 divided by cos h square u into du by dx, which is equal to sec h square u into du by dx. In a similar manner, we may establish the rest of the formulas in the following list. d by dx of tan h u is equal to sec h square u into du by dx, d by dx of cot hu is equal to minus cosec h square u into du by dx. d by dx of sec hu is equal to minus sec hu into tan hu into du by dx. d by dx of cosec hu is equal to minus cosec hu into cot hu du by dx. Each of these derivative formulas has a matching differential formula. This in turn may be integrated at once to produce the following integration formulas. Integral sin hu du is equal to cos hu plus c. Integral cos hu du is equal to sin hu plus c. Integral sec h square u du is equal to tan hu plus c. Integral cosec h square u du is equal to minus cot hu plus c. Integral sec hu into tan hu du is equal to minus sec hu plus c. Integral cosec hu into cot hu du is equal to minus cosec hu plus c. Example. Obtain the value of d by dt of tan h root of 1 plus t square. Solution. We have d by dt of tan h root of 1 plus t square is equal to sec h square root of 1 plus t square into d by dt of root of 1 plus t square. That is equal to 1 divided by root of 1 plus t square into sec h square into root of 1 plus t square. Example 2. Show that y is equal to a into cos h x by a satisfies the differential equation d square y by dx square is equal to w by h into square root of 1 plus dy by dx whole square, provided a is equal to h by w, where h and w are constants. Solution. By differentiating y is equal to a into cos h x by a, we find dy by dx is equal to a into sin h x by a into 1 by a, that is equal to sin h x by a. d square y by dx square is equal to cos h x by a into 1 by a. We substitute this into d square y by dx square is equal to w by h into square root of 1 plus dy by dx the whole square, and obtain 1 by a into cos h x by a is equal to w by h into square root of 1 plus sin h square x by a is equal to w by h into square root of cos h square x by a, which is equal to w by h into cos h x by a, since cos h x by a is greater than or equal to 0, which is a true equation provided a is equal to h by w. Example 3. Evaluate integral cot h 5x dx. Solution. Integral cot h 5x dx is equal to integral cos h 5x by sin h 5x dx, that is equal to 1 by 5 into integral du by u, where u is equal to sin h 5x, that is equal to 1 by 5 into log mod u plus c, which is equal to 1 by 5 into log mod sin hx plus c. Example 4. Evaluate integral from 0 to 1 sin h square x dx. Solution. From the identity cos h 2x minus 1 is equal to 2 into sin h square x, we have sin h square x is equal to cos h 2x minus 1 all divided by 2. Therefore, integral from 0 to 1 sin h square x dx is equal to integral from 0 to 1 cos h 2x minus 1 all divided by 2 dx, that is equal to sin h 2x divided by 4 minus x by 2 between the limits 0 and 1, that is equal to sin h 2 by 4 minus 1 by 2, which is approximately equal to 0.40672. Example 5. Evaluate integral x into sin hx dx. Solution. Integration by parts, we let u is equal to x, dv is equal to sin hx dx, v is equal to cos hx, so that integral x into sin hx dx is equal to x into cos hx minus integral cos hx dx is equal to x into cos hx minus sin hx plus c. The inverse hyperbolic functions. Since d by dx of sin hx is equal to cos hx is always positive, the hyperbolic sign is 1 to 1 over its entire domain minus infinity less than x less than infinity. It therefore has an inverse which we denote in the usual way by y is equal to sin h inverse x. The minus 1 in sin h inverse x does not mean reciprocal, it means inverse. For every value of x in the interval minus infinity less than x less than infinity, the value of y is equal to sin h inverse x is the number whose hyperbolic sign is x. We call sin h inverse x the inverse hyperbolic sign of x. The hyperbolic sign is an increasing function of x. The function y is equal to cos hx is not 1 to 1, but the restricted function y is equal to cos hx where x greater than or equal to 0 is 1 to 1 and therefore has an inverse denoted by y is equal to cos h inverse x. For every value of x greater than or equal to 1, y is equal to cos h inverse x is the number in the interval 0 less than or equal to y less than infinity whose hyperbolic cosine is x. The hyperbolic tangent, cotangent and cosecant are 1 to 1 on their domains and therefore have inverses denoted by y is equal to tan h inverse x, y is equal to cot h inverse x, y is equal to cosec h inverse x. The inverse hyperbolic secant, cosecant and cotangent satisfy the identities sec h inverse x is equal to cos h inverse 1 by x, cosec h inverse x is equal to sin h inverse 1 by x, cot h inverse x is equal to tan h inverse 1 by x. The inverse hyperbolic tangent is given by y is equal to tan h inverse x, which is equal to 1 by 2 into log 1 plus x divided by 1 minus x, where mod x less than 1. Here the variable x is restricted to the domain mod x less than 1, since x is equal to tan hy lies in this interval for all real values of y where minus infinity less than y less than plus infinity. Example 6. Tan h inverse of 0.25 is equal to 1 by 2 into log of 1.25 by 0.75, which is equal to 1 by 2 into log of 5 by 3, which is equal to 1 by 2 into log 5 minus log 3, which is approximately equal to 0.25541. The expression for the other inverse hyperbolic functions in terms of logarithm are found in a similar manner. They are sin h inverse x is equal to log of x plus square root of x square plus 1 for minus infinity less than x less than infinity. Cos h inverse x is equal to log of x plus square root of x square minus 1 for x greater than or equal to 1. Sec h inverse of x is equal to log of 1 plus square root of 1 minus x square all divided by x, which is equal to cos h inverse of 1 by x for 0 less than x less than 1. Cosec h inverse x is equal to log of 1 by x plus square root of 1 plus x square all divided by mod x is equal to sin h inverse of 1 by x for x not equal to 0. Cot h inverse of x is equal to 1 by 2 into log of x plus 1 by x minus 1, that is equal to tan h inverse of 1 by x for mod x greater than 1. Example 7. Prove that cos h inverse x is equal to plus or minus log of x plus square root of x square minus 1. Solution. Let y is equal to cos h inverse x. Then x is equal to cos hy, which is equal to 1 by 2 into e raised to y plus e raised to minus y. That is, e raised to y plus e raised to minus y is equal to 2x. That is, e raised to y is equal to 2x plus or minus square root of 4x square minus 4 all divided by 2. That is equal to x plus or minus square root of x square minus 1. Or y is equal to log of x plus or minus square root of x square minus 1. Since log of x minus square root of x square minus 1 is equal to log of x square minus of x square minus 1 all divided by x plus square root of x square minus 1 is equal to minus log of x plus square root of x square minus 1, the required result follows. Note that we must have x greater than or equal to 1 if y is equal to cos h inverse x is to be real. Derivatives and integrals of inverse hyperbolic functions. D by dx of sin h inverse u is equal to 1 divided by square root of 1 plus u square into du by dx. D by dx of cos h inverse u is equal to 1 divided by square root of u square minus 1 into du by dx. D by dx of tan h inverse u is equal to 1 divided by 1 minus u square into du by dx for mod u less than 1. D by dx of cot h inverse u is equal to 1 divided by 1 minus u square into du by dx for mod u greater than 1. D by dx of sec h inverse u is equal to minus du by dx divided by u into square root of 1 minus u square. D by dx of cosec h inverse u is equal to minus du by dx divided by mod u into square root of 1 plus u square. Proof. The proof of all these follow the same method. Here we illustrate the case of cos h inverse u. To this end, let y is equal to cos h inverse u. Then cos hy is equal to u. Sin hy into dy by dx is equal to du by dx. Dy by dx is equal to 1 divided by sin hy into du by dx. But cos h square y minus sin h square y is equal to 1 and cos hy is equal to u. So that sin hy is equal to plus or minus square root of cos h square y minus 1, that is equal to plus or minus square root of u square minus 1, and dy by dx is equal to 1 divided by plus or minus square root of u square minus 1 into du by dx. Integration formulas. 1. Integral du divided by square root of 1 plus u square is equal to sin h inverse u plus c. 2. Integral du divided by square root of u square minus 1 is equal to cos h inverse u plus c. 3. Integral du divided by 1 minus u square is equal to tan h inverse u plus c if mod u less than 1 and cot h inverse u plus c if mod u greater than 1, that is equal to 1 by 2 into log of mod 1 plus u divided by 1 minus u plus c. 4. Integral du divided by u into square root of 1 minus u square is equal to minus sec h inverse mod u plus c, that is equal to minus cos h inverse 1 by mod u plus c. 5. Integral du divided by u into square root of 1 plus u square is equal to minus sec h inverse mod u plus c, that is equal to minus sin h inverse of 1 by mod u plus c. The main use of inverse hyperbolic functions lies in integrations that reverse the derivative formulas. The restrictions mod u less than 1 and mod u greater than 1 on the derivative formulas for tan h inverse u and cot h inverse u comes from the natural restrictions on the values of these functions. The distinction between mod u less than 1 and mod u greater than 1 becomes important when we convert the derivative formulas into integral formulas. If mod u less than 1, the integral of 1 divided by 1 minus u square is tan h inverse u plus c. If mod u greater than 1, the integral is cot h inverse u plus c. Example 8. Evaluate integral from 0 to 1, 2 into dx divided by square root of 3 plus 4x square. Solution. We have the indefinite integral du divided by square root of a square plus u square is equal to sin h inverse of u by a plus c. Put u is equal to 2x, du is equal to 2 into dx, a is equal to square root of 3. We get integral 2x dx divided by square root of 3 plus 4x square is equal to sin h inverse of 2x by square root of 3 plus c. Therefore, integral from 0 to 1 to dx divided by square root of 3 plus 4x square is equal to sin h inverse of 2x divided by square root of 3 between the limits 0 and 1. That is equal to sin h inverse of 2 by square root of 3 minus sin h inverse of 0. That is equal to sin h inverse of 2 divided by square root of 3 minus 0, which is equal to 0.98665 approximately. Let me conclude this session. In this session, we have defined hyperbolic functions and inverse hyperbolic functions. Also, we discussed the derivatives, integrals and identities involving of these functions. We have seen that the hyperbolic functions bear a number of similarities to the trigonometric functions after which they are named. Now, you may try to answer the following questions. First one, find dy by dx if a. y is equal to sin h 3x, b. y is equal to cos h square 5x, c. y is equal to cos h square 5x minus sin h square 5x, d. y is equal to cot h of tan x. 2. Evaluate a. integral cos h 2x plus 1 dx, b. integral tan hx dx, c. integral sin hx by cos h raised to 4x dx, d. integral 4 dx divided by e raised to x plus e raised to minus x the whole square, e. integral e raised to x minus e raised to minus x all divided by e raised to x plus e raised to minus x dx, and f. integral tan h square x dx. 3. Find dy by dx if a. y is equal to sin h inverse of 2x, b. y is equal to tan h inverse of cos x, c. y is equal to cos h inverse of sec x. 4. Evaluate a. integral dx divided by square root of 1 plus 4x square, b. integral dx divided by square root of 4 plus x square, c. integral from 0 to 0.5 dx by 1 minus x square. 5. Use trigonometric substitutions to evaluate the integrals a. integral du divided by square root of u square minus 1 where u greater than or equal to 1, b. integral du divided by u into square root of u square minus 1, c. integral du divided by u into square root of u square plus 1. Let me suggest a few books for your higher study. First one, Calculus, 9th edition by George B. Thomas, Rosal Finney, Pearson's Education, New Delhi, 2002. Second one, Theory and Problems of Advanced Calculus, Shom's Outline Series, Shom Publishing Company, New York. Third one, Integral Calculus, Gorak Prasad's Pothshala Private Limited, Allahabad. Fourth one, Differential and Integral Calculus, N. Piskunov, Mir Publishers, Moscow. Hope that you have enjoyed this session. We will meet again with another topic. Thank you.